Good day. Today we will discuss our problem solving about resistance, and my pedagogy or methodology and how I will do this is I will flash here on the screen the problem, and then we will discuss the solution of that problem. Okay, so as you can see here in the screen that we already have that problem. Okay, so I will read it out for you. What is the resistance of a 100 feet length copper wire with a diameter of 0.02 inches at a temperature of 20 degrees centigrade? Okay, so the solution will be this. Okay, so in this problem we have two possible solutions. First solution is a long method, and the second solution is the shortcut method. Okay, let's have the first method, long method. The long method has a solution in terms of metric units. So here, from basement of problem, we have a constant of resistivity at 20 degrees centigrade. So you do not need, you need to memorize this one if the problem does not have resistivity. As you can see here, on the problem, there is no resistivity, so therefore the resistivity is already a constant parameter that we have already tackled from the basic principle and concepts, and that is 1.72 times 10 to the negative 8 ohm meter, ohm-meter, or metric unit. Okay, now since we already have the resistivity, we need to compute for the area. However, in this problem, it's not mentioned if that is a stranded conductor, a round conductor, perfect conductor, but it's very basic, and it is common sense already that you can assume that this is a round conductor. Okay, so if you have a solid round conductor, the formula for the area of a circle is equal to pi over 4 d squared. Okay, so since we already have a given of 0.02 inch, you need to convert it to its corresponding meters, by having these conversion factors. In 1 inch, you have 2.24 centimeter. In 1 meter, 100 centimeters. So it will cancel, okay, those units there, giving us a metric squared unit. So the unit is metric squared. The answer here is 0.02 times 10 negative 6, or micrometer squared. Okay, now if you already compute for the area, we will compute for the length. So the length is 100 feet here, which is in English term. So 100 feet converted to meter, okay, will cancel feet here, and then we will have 30.48 meters. So since you have a meter here and a meter squared here and an ohm meter, all of the units are already converted to metric. So you can now use the first formula on our basic fundamental, that RDC is resistivity times length all over the total area. So since all of this are already in metric units, so you can already substitute all of those parameters. So here, to check it out, you have ohm meter for resistivity, the length is meter, and this is meter squared. So yes, the meters will cancel out, giving us behind rather an ohm value. So the answer here is a 2.6 ohm resistance. Now we will discuss the shortcut method, and this is the alternative way to solve problem number 1. So the long method, we use metric units, and we converted two parameters. The first parameter length, then the second parameter area, then you solve for the resistance. However, in this method, we only we will only use the basic formula of the area of Siemens that we have discussed in the basic principles. So the shortcut method will use an English method. So English method, or English units method, that the units is in terms of inch, mils, or feet. So in this case, as I have mentioned, you need to memorize the constant So this is a constant that we have discussed on the basic fundamental that the resistivity of copper, and this for copper, here is 10.37 ohm circular mil per feet. And since we have a round conductor, we can already assume, that the copper is round. So in this case, the area of C mills can be converted by the diameter in terms of mil squared. So what you will do is the diameter here, okay, which is 0.02 inch, must be converted to to mils squared. So that will become circular mil. So hence this will become mil squared, and then the diameter here, okay, will be the numerical value. So the numerical value will have a 400 value here, and it is already in circular mils. So please take note, you can use this method if you have your diameter, round conductor, or perfect conductor, and it must be in terms of mils. Okay? And then you square it with a circular mil. Okay, so that's the reason why it is a shortcut method, because you only, okay, converted one parameter, which is the area. So hence, going forward to our basic formula for resistance, rho L over A total or area total, you have 10.37 ohms C mil per feet, length 100 feet from the given, and 400 circular mil. It will cancel circular mils here, the feet here, leaving behind the unit of ohms. And thus, by having your calculators, practice that out, you will have this value here in RDC at 20 degrees centigrade, 2.59 ohms or 2.6 ohms. So when we compare it to the last problem, you have a 2.6 ohms. And again, usually use chipips. Say chipips means we have an easy solution and then we got the correct answer. Chipips kapatid. Now, we will discuss problem number 2. Okay, and this flash on your screens here. Okay, problem number 2, I will read it again. What is the resistance of a copper bus bar in micro ohms as used in the power distribution panel of a high-rise office building? The specification of or dimension of this bus bar is a 3 feet by 5 inch by 0.5 inches. So our main goal here, okay, this is the solution, okay, of the problem here. We have a bus bar which is a rectangular shape. So it means, so this is non-circular, of course. Now we need to get the resistance of this bus bar. Remember, bus bars are not always round, but they are in terms of a rectangular shape, so that you have the height, width, and the length, which constitute, if you multiply all of those, constitute a volume. But our main goal here is to get the cross-sectional area converted to C mils. So what we will do first is we need to convert the values here, okay, of 5 inches and 0.5 inch to its corresponding mils value. So here, 5 inches, okay, there is 1,000 mils in 1 inch, you have 5,000 mils. Okay, hopefully you can see it, okay. And then you have 0.5 inch, you have 0.5 inch times 1,000, you have 500 mils. So you already have the height and the width converted to mils. Okay, first is you need, okay, the solution properly. First, you need to compute for the cross-sectional area. So the cross-sectional area is height times width. So therefore, you have 5,000 times 500. You have a 2.5 million square mil. So this one is also, mil squared is square mils. Considering again, the units. Okay, one formula that we have discussed, from the fundamentals is you can convert, okay, the cross-sectional area, to its corresponding circular mil, okay, by having this relationship. Okay, C mils area, mils is in terms of the corresponding length. So square mil is the area in the area of the rectangle. Then you need to convert it the area of a circle. So if you have a 2.5 times 10 to the 6 square meals, and you have this relationship, the square meal will cancel out, then the value will become an area of a circle in terms of circular meal. The answer is 3.183 times 10 to the 6 circular meals, or 3.183 million circular meals. Continue with problem number 2. So we already established the area from the last slide. And we already have this one in terms of circular meal, 3.183 million circular meal. Okay, so we already have the length, which is 3 feet, and your constant. So don't forget again this constant here, which is pure resistivity of the copper bus bar. Okay, multiplying those values there, and then cancel the units as usual. You need to know the units as well here so that you can see what is the resulting unit. The unit is ohms. And hence, therefore, the RDC is 9.77 times 10 to negative 6 micro ohm, or approximately 0. So you're just wondering, a copper bus bar having 0 resistance, so that you will have a larger current. One reason why you need to have, a negligible resistance here is to prevent losses. Because if you have larger resistance, you will have larger voltage drop or power loss. So you do not need to have those losses, because it will greatly affect the performance of the system. So it's very reasonable that our resistance here is approximately 0 to prevent larger losses. We will go to problem number 2. Okay, now we will continue our discussion on problem number 3. So before we proceed with problem number 3, we need to read the problem first. Okay, so the resistance of a cylindrical brass conductor, 0.5 centimeter in diameter and 3 meters long, is 0.0108 ohms. We need to determine the resistance of this cylindrical conductor of the same material at the same temperature and having a diameter of 0.25 centimeter and a length of 8 meters. So the solution is this. Okay, now, so to solve the problem, first is we need to know the given of the problem. Okay, the problem has a given of length 1 d1 and length 2 d2, and this is the diameter 0.5 centimeter, length 1 3 meters, resistance of 0.0108 ohm, and we have the diameter at the second condition as 0.25, length of 2 at 8 meters, and this is the required in the problem. Okay, the resistance. By the way, I forgot to mention from the previous slides that I have a PDF link that you can see, on the description of the video. So you can click it down, click it out, and then you can see the problems so that you can review. And then I have also some supplementary problems for you to solve. And it is already have an answer. So you need to practice the principles so that you can fully understand and review the fundamentals that we have discussed on the previous slides. Okay, let's go back to the solution proper. So the solution here is have the first area, pi d squared all over 4. So in terms of first diameter. So the area here, by substituting 0.5, you have 0.1963 centimeter squared. You will also do the same process for the second area, okay, here in the second condition. So pi d squared over 4, and pi over 4.25 squared, we will have a 0.049 centimeter squared. So the technique here is when I discussing this solution, you can have your calculators or jotting notes. Because jotting notes will give you, three times the learning you see, you hear, and you write. Okay, so that's three times the learning. Okay, so from there, go forward to the basic formula of resistance. This resistance, go L over A. So our main goal here is to get the resistivity. Okay, so resistivity is area times resistance over the length. So substituting all of those values, okay, 0.1963, 0.0108 ohms, 3 meters, but you need to convert it to centimeter here because the length is in 3 meters. Okay, it will cancel the majority of the units, leaving behind ohm. So the answer is 7.067 micro ohm centimeter. Okay, what's the meaning of this and what is the importance? If you read the problem carefully, sorry, you have the same material. So if you understand the basic principle, no, before we go to the problems, that when you say same material, it means that you have a same resistivity. Same resistivity. Okay, it means same material. They are, both of them are copper, both of them are aluminum in the condition. Or both of them are steel conductors. So it depends on the resistivity. Now, since we have we do not know what is that material, so we can now solve for that resistivity. Okay, at the first condition, and we have this result, and this result will also be your resistivity at the second condition. Now you can solve. You can now solve for the resistance. Okay, to conclude the last problem, which is problem number 3. So we already have the resistivity that is computed from the last slide. So the resistivity is 7.067. I forgot the Einstein negative 6 here. Okay. 7.067 times 10 negative 6 or micro ohm centimeter. So, from our basic formula of resistance, that R2 is equal to rho 2 L2 all over the area 2. We already have this one, and we already computed this from the last solution. So, we already have 7.067 micro, 8 meters converted to its corresponding centimeter. And then the area 0.049 centimeters squared. So the majority of the units will cancel out and leaving behind an ohmic value of ohms. The answer for this problem is 0.1154 ohms. Hello. So we need to continue our problem solving. We are already in problem number 4, I think. So let's read the problem first. Problem 4. A uniform wire is to be made from 1 kilogram of copper, and if this wire is to have a resistance of 0.02 ohms, and if all of the copper is being used, what will be the size of this wire in millimeter squared? And for the copper, the resistivity is 1.7 times 10 negative 8 ohm meter, and the mass density is 8920 kilogram per metric cube. Okay, this is the solution in the problem. So first, we need to know the given. The given is mass is 1 kilogram. The density is 8920 kilogram per meter cube. And we already know that copper is 1.7 times 10 negative 8. If you forgot the resistivity, then we already know those constants already from the previous problem. Okay, actually this problem here is a former board exam problem. So that this is a very interesting problem. In this case, we need to know first the density formula, that's mass all over volume, and we need to interchange that so that we can get the given, the volume required rather. So the volume here is 1 kilogram, then the density divided by density, that's 89 kilogram per metric cube. So it will cancel the kilogram, and then we will have the metric cube value. So the volume is 1.121 times the negative 4 raised to cubic meter. Okay, we need to know the formula of the area. Okay, the resistance formula is RDC is rho L all over A, but we know that the volume is area times length, and then we need to get length so that we can substitute there on the resistance formula so that we have a formula in terms of resistance, the volume, and in terms of area as well. So the length is V all over A, and then substitute the length there so that it will have this formula in terms of resistance. Another formula of resistance in terms of volume and area. That is resistivity times volume all over area squared. Now we can now get the area here, which is the square root of resistivity times volume all over R. Okay, we will continue our lesson, continuation of problem number 4. So from our previous slide, we already have the area, which is simply equal to the square root of resistivity times volume all over the corresponding resistance. So what we have done here is I just substitute the resistivity here, 1.7 times 10 negative 8 ohm meter, and then the volume, 1.121 times 10 negative 4 meter raised to metric cube, u divided by 0.02. So the ohms will cancel out. And you can see here the remaining units is metric to the fourth. So get the square root, then you will have the area in meters squared. So if you calculate it on your calculator, so the answer is 9.76 times 10 to negative 6 meters squared. So you need to convert it to millimeters squared by having 1 millimeter, you have 1,000, 1 meter rather, is 1,000 millimeter, and then you square it. So the remaining unit is millimeters squared. So hence the final answer here, if we calculate this, is 9.76 millimeters squared. Okay, I think this will be the final problem. So if you want to have the copy of the problems for topic 1.1, which is resistance, you can download it on the description page, description of the video. I can give the Google link, plus as well as the supplementary problem. So you need to practice the supplementary problem so that you can have the mastery of the subject matter. So what will you anticipate on my next video will be lesson 1.2, which is resistance versus temperature. Hope to see you there. Thank you and have a nice day.